This is Geometry, Chapter 9, Lesson 9, page 677. And actually, I want to go to page 678. So this entire chapter has been about solids. But we've not talked at all about particular names of three-dimensional objects and how many faces they have, how many vertices they have, how many edges they have. So that's what we're going to do for this lesson. And it will be important for you to know these names of these polyhedron. All right, so it's a polyhedron because it exists in space and it's three-dimensional. A polygon is 2 dimensions and it exists on a plane. A polyhedron is made up of intersecting planes. Those planes intersect where the edges are and the vertices lie. All right? And we're going to talk about Euler's formula for the polyhedron that you will have to know. All right? So look at the definition on page 678 of what a regular polyhedron is. You can anticipate by the word regular and polyhedron, right? It has to be convex. It has faces that are congruent polygons. And it has an equal number of polygons at every vertex. So if at one vertex there are 3 polygons, then at every vertex there are 3 polygons that intersect to make that vertex. All right, so look at the tetrahedron. How many faces on a tetrahedron? There are 4 faces on a tetrahedron. How many edges on a tetrahedron?
6.
There are 6. There are 6 edges. Triangular, right. How many vertices? How many? 4. That is correct. So Euler's formula for every polyhedron says that if I take the number of vertices, add to it the number of faces, subtract the number of edges of any regular polyhedron, the result will always equal 2. So I could give you the faces and the edges and ask you how many vertices there are, and you could figure it out. All right, so let's do that on the tetrahedron. Vertices, we said there were 4. Faces, we said there were 4. Subtract the number of edges, and we do in fact get 2. Okay, is that not amazing to you that that is true for every polyhedron, regular polyhedron, no matter how many planes make up that polyhedron? That to me is an amazing fact that always stands true. Okay, so if there are 4 faces, you have to know that it's a tetrahedron. You have to know that. Like, you have to know 4 faces is a tetrahedron. The next one is an octahedron. How many faces are on an octahedron? 8. That's correct. How many vertices does an octahedron have? How many? 6. There's one we do not see, right? 1, 3, 4, 5, 6. Vertices. There's one that we do not see. How many edges? There are 12 edges. So if we take the vertices that we said 6 plus 8, which is 14, minus 12, does in fact equal 2. The next one is an icosahedron. Icosa means, do you know what icosa means? 20. That's right. Icosahedron has 20 faces. Okay, it would be hard to count them, but does anybody count the vertices? It's hard to figure out how many you don't see.
12.
There are 12 vertices, and edges you could calculate. There are 30 edges. 30 edges. A cube. Typically when you think of cube, you think of what? What did you say?
A square.
You think of a square, right? How many faces does a cube have? 6. How many vertices? It has 8 edges. 12. 4 on the bottom, 4 on the top, 4 in the middle. The cube is the easiest. And the last one is a dodecahedron. A dodecahedron. How many faces does a dodeca have? 12. That's right. How many vertices does that dodecahedron have?
72.
Vertices? More than 17.
72.
20. Who has 20? Very good. And the edges, how many edges? 30 edges. That's right. You could calculate it, couldn't you? To me, it is extremely interesting that an icosahedron and a dodecahedron have the same number of edges. Why would that be so? Why would an icosahedron and a dodecahedron have the same number of edges? Look at them. There are more faces in an icosahedron than a dodecahedron, but why would there be the same number of edges? Yes.
Triangle, not a.
That's right, because the planes on an icosahedron are triangular. There's only 3 edges, right? But on a dodecahedron, it requires a pentagon, 5-sided, so there are more edges to meet. Does that make sense? All right.